Okay, so can you guess the correlation? What does the correlation R tell us about the relationship between two quantitative variables? Okay, so right here, it's going up, so that is positive. Okay, I know, I told you, best day ever. Now, we are going to say it is fairly strong, because remember, in AP Stat, we are not absolute. Yes. All right, over here, is this negative or positive? Negative. We're gonna call this no, false. Moderately negative. All right. What about this one? Is it positive or negative? Oh, no, no. Very strong. Negative. I know. Yeah. All right. What about this one? No. Weak. Positive. All right. What about this one? Almost no correlation. All right. On this one, positive or negative? Negative. And it is moderately negative. Okay, so how do you tell? If it's between like 0.6 to 0.7, that's moderate. Yeah. If it's really close to 0, you're going to say almost no correlation. If it's between like 0.15 to like 0.4, that's going to be weak. And then very strong is going to be close to 1. Like a half and half relationship. You could say like moderately. So if it's from 0 to like 0.15, we're going to say almost no correlation. If it's like 0.15 to like 0.40, we're going to say moderately. Okay. If it's like 0.6 to like 0.8, we're going to say, ooh, sorry. Hang on. Pause. Yep. Weak. And then moderate. And then from like 0.85 to like 0.99, we're going to say strong. Again, nobody's going to like hold you like firmly to these. Huh? Fairly is thrown in there because it's not super strong, but it's like fairly strong. Like we're getting close to it. Yeah. Like you want to use positive or negative, and then strong or weak. Those are like good buzzwords. Yep.
We're really getting to the business side now.
I feel like correlation is like great and terrible all at the same time. Like who needs to put all these dots on one thing? Good? All right. All right, so what do you think the correlation R is measuring? Go ahead, Mo.
I'm sorry, but I'm still a little confused.
On.
So if it's like 0.45, then
You could say like weak to moderate.
like,
Weakly moderate.
like average. So like if it looks pretty weak, you can say weak. Like you just like say just keep it accurate, but then it's like
Whatever looks pretty, I'm done.
look at it, be like, hey, this is pretty weak.
Is it strong? Is it weak? Is it positive or negative? That's it.
I have to do that.
I feel like it's just kind of made up at this point. All right. So what do you think the R correlation is measuring? It's how close to a line closely a point follow a line. Strength of a linear relationship. And just like what David said, line of best fit. It also tells us the direction. We often talk about positive or negative, right? So, class, on the next one, is it positive or negative?
Positive.
Okay, good. Is it weak, moderate, strong, or very strong? Good, class. Now, what's the R value?
I know, 0.7.
It's not 0.7. We could say like 0.5. We could say 0.6. So we could say like 0.5 to 0.6. Okay. All right, class. What's the next one? Oh, so good.
Very strong.
How'd you know?
Out.
All right, so what about the correlation? What's the R? Okay, so negative 0.99, negative 0.97. Right? We don't want to say 1. What would 1 would be a complete straight line, right? And they would have to be exactly in a straight line in order for that to happen. What if the Earth is flat? Okay, go ahead and flip the page. Flip the page. Okay, so tomorrow we're gonna chunk Barbies off the ledge. But here is some data from the Barbie bungee. Okay, so R equals 0.987 and R squared is 0.974. All right, after class, the group measured the distance traveled for 12 rubber bands. How will adding this point to the scatter plot affect the correlation? So adding this one right here. What did it do? We want to look at the correlation, the pattern. So instead of it going here, if we connect that line. Sal, what do you mean it strengthened? It's spread out? We don't want to look at it from here to here. We want to look at it, is it closer to the line? So R will get closer to 1 because the data becomes more linear. Yes.
Then it's the far away.
Right.
I don't have to follow up on that,
Mhm.
but we're basically guessing like it lists what it's considered seven possible.
That line is terrible. Okay, the group accidentally typed 85 centimeters for 5 rubber bands instead of 58. I know, failure. How will this point affect the correlation? Okay, so this guy right here. So the R will go down because the point makes data less linear. Yes.
Like this week, bro, are you slow? Oh, dang, that's crazy.
Who knows, like, okay, this is your test. This is your test on chapter 3. We won't quiz until after. We'll probably do it the 3rd. Mo is locking in, just in case you're wondering. All right. So template for interpreting correlation. So here's a little sentence that you got to remember for this unit. So the linear relationship between the explanatory variable and the response variable is whatever the strength and the direction is. So we're going to interpret the R for the given Barbie data at the top of the page. So what was the R value at the top of the page? 0.987. Okay, so what we're going to write is the linear relationship between the number of bands and distance traveled. Is it strong, very strong, moderate, or weak? Oh, so good, class. And is it positive or negative? Hey, man, do good. See, y'all don't even need me here. I should go home. That's right. Yeah, yeah. 3 days in a row.
11:14.
Oh,
Didn't. I'm so sorry. I'm gonna be honest though. Yesterday, I didn't have internet, and I thought about it. I was like, I need to get those YouTube videos uploaded. And I tried to like log in and like connect to a hotspot, and that didn't work. And then I was like, you know what? No, that's not what I said. That's not what I said. I just got to a point where I was like, I can't do anymore. Done. So respectfully, I tried. I did try. It was there.
yeah, I think I'm pretty good.
I look a little silly.
I know.
All right, ready? R squared percent of the variation in the response variable is explained by the linear relationship with the explanatory variable. So we're going to interpret. So R squared, we said at the top of the page, was 0.974. Okay, so that means that 97.4% of the variation in distance traveled is explained by the linear relationship with the number of rubber bands. Okay, so tomorrow, remember, you're bringing some type of action figure slash Barbie that you're okay with chunking off the side of.
Brown.
I mean, if you put enough rubber bands, yeah. I would do something, I would do Barbie-esque type thing.
Can I do a Lego?
No, that will shatter into a million pieces.
That'd be my top. Like a Lego beach.
Yeah. Okay, you're wanting to use the Barbie though. Like you're gonna want to use like a Barbie. Yes. You don't have a G.I. Joe doll? You don't got a Marvel character? A what? No. I have a couple, and we can share. We can make bigger groups than two, but if everybody plans on bringing one, then we'll have more than that.
Right. He's very stable.
No.
He's technically an action figure. He's like EA.
Oh my God. No. Barbie doll G.I. Joe-esque thing. You don't know what a G.I. Joe is? Right there, Mo. Right there, Mo. Do you? There you go. Most Barbie dolls actually cause that. All right, flip page. Let's go. All right. So we talked about correlation, which is R. We talked about the direction, which is positive or negative. Okay. And then we talked about strength. And that's between -1 to 1. If it's anything over than that, wrong. Okay. And then we talked about our little statement. We said the linear relationship between X and Y is strength and direction. Okay. And then we talked about R squared. We talked about a little statement, the percent of the variation in Y explained by the linear relationship with X. And correlation does not mean causation. For instance, just because you get more sleep doesn't mean that your grades go up. They're highly correlated or moderately correlated, but does not mean that one causes the other, because there are people in the world who get a lot of sleep that don't do anything and then they fail their classes. Some deep little guy. All right, go ahead and try ABC. Go. And this, like this unit, this one, this is the one to do well on. This is the one to do well on. Okay. I don't want to say that. Ready? Let's go. All right. So this dude wrote this book called Spurious. Spurious? Is that Spurious? How do you say that word? There it is. In which he investigates relationships between quantitative variables. One example is the strong correlation between the number of letters in the winning word of the National Spelling Bee and the number of people who died from venomous spider bites in a given year. Yep. Here are the data for 11-year span. Okay, so the correlation between the number of letters in the winning word of the spelling bee and the number of deaths is R equals 0.806. Wild. All right, so interpret this value. A linear relationship between word, letters, and deaths by spider. Is it strong, fairly strong, moderate, or weak? Fairly strong. Is it positive or negative? And it's positive. All right. Questions on that one? That's a little statement that you got to have memorized. Linear relationships between word, number of letters in the word, and deaths by venomous spiders is fairly strong and positive. Okay, ready? Okay, talking about coefficient of determination. A lot of times they like to use, instead of R squared, they'll say coefficient of determination. That's R squared, not R. Make sure that you pay attention and know that. Okay? So calculate and interpret the coefficient of determination. R squared, we're just going to take R and square it. I know. Thank you for your reaction. That was amazing. I was like, whoa. All Okay, so we're gonna say about 65% of the variation in deaths by spider bite can be explained by the linear relationship with letters and words. What? What did you say? So what did we learn? We learned that we should pay attention to the math instead of having side conversations. Bo. All right, here's the important part. Ready? So there is a strong correlation between these two variables. Does this mean that the longer winning words in the national spelling bee caused an increase in the number of deaths by venomous spider bite? No. Okay. So strong correlation does not mean that one caused the other. Okay. You know, this is crazy. Oh my God. Oh, okay. So there's this little like book that this guy wrote, Furious Correlations. It's actually a website. And so when you go on here, I'm gonna delete this and put it back. For instance, here are two correlations. The popularity of the slaps roof of car meme. I don't know which one that is, but we're not pulling it up because I don't trust you anymore. Oh, got it. Okay, got it. That was okay. And the divorce rates in the United Kingdom. So like he just basically put those two things on the same map. So I thought that was kind of cool. Here's another one. Number of breweries in the United States and the solar power generated in Peru.
Got it.
Bachelor's degree awarded in library science and the ticket sales for Oakland athletic games. I don't know. Oh, dried manure used for fertilizer in the US and customer satisfaction with Target. It's all over the place. All right, so he does have that website if you wanted to take a look. Some of them are kind of funny. It's like Nick Cage related to like everything in the world. So yeah. Yeah. Have y'all ever heard of like 7 levels of Kevin Bacon? Kind of like that. That's how correlation goes along. All right. End of the page. Oh, you were doing so well. Okay. So let's do another easy one because that one wasn't bad, right, class? Right, class? Okay, cool. I'm glad we had that talk. Okay. So you're gonna need a laptop. Yeah, I'm not doing it for you. Okay, so you're gonna go to statsmedic.com/applets and you're gonna make a scatter plot. And we're gonna calculate the least squares regression line, also known as LSRL. They use that abbreviation a lot. Least square regression line. Okay, so I'm gonna take it out your laptop. No, we're gonna fight. On. Oh, no. Alex, pay attention. Hey, hey, get your laptop out.
Yes, sir. Oh, yes, ma'am. Oh, yes, ma'am. Oh, ma'am. Yes, ma'am. Yes, ma'am. Oh, yeah. Oh, yes, ma'am.
Super bruised, Joe. Thank you. You're gonna go to list and type the chart in. And then you're going to go to menu. So you're gonna go to menu. And then you're gonna go to analyze. Is that an option? No. All right. So you're gonna go to statistics. So number 6. And then you're gonna go to stat calculations. That's it. And then you're gonna type linear regression. So you're gonna go to menu, stat. What was the next part? Stat calculations. And then you're gonna type in your list names. Okay, we're gonna watch this part. So you're doing the mx plus b one. So linear regression. Everybody good so far? Missing number? What do you think it's gonna be? Somewhere between 55 and 69. So pick a number in between 55 and 69. Okay. Okay, so you're gonna label your X and Y and then click enter. Okay, when you do that, it's gonna pop up like this. Okay, so go ahead and hit enter. And when you do that, you should have gotten this equation. Um, there it is. I was like, what is going on? All right, you should have gotten 25.23 plus 7.46x. These two numbers should have been in that little column. Is that what you got? Roughly? Okay. So what does this actually mean? This means distance equals 25.33 plus 7.46 times the number of rubber bands. So then now, to answer Rebecca's question, what is the predicted distance for the number of rubber bands being 5? Well, we're going to take this equation and plug in 5. And when you do that, you get about 6.63, 52.63 centimeters. Plus But one of the group members later found that the measurement for 5 rubber bands was 64. Was the actual value above or below the prediction? How far off? So we're going to take 64 and subtract 62.63. Say again. Okay. I was like, what? 64 minus 62.63. You're going to get 1.37. This is what we call a residual. We talked about that briefly. We have not gone into it too much. So that's where you have your actual minus your predicted. All right, number 4, predict the distance that the Barbie would travel if the group used 20 rubber bands. Would you trust this prediction more or less than the prediction you made in number 2? So y equals 25.33 plus 7.46 times 20. We would get 174.53. Would we trust this more or less? Would we trust this more or less?
As you reduce your sensor size, get closer to
But we only have this data, right? We're not adding to the data. So if we only have this data, we're going to trust this less. Okay? That's okay. It's far from our data. This is what we call extrapolation. You cannot predict the future, but what you can talk about is the sample that you took. Okay? But oftentimes we like to say like one sample is all the evidence you need for future indication, right? You know, we always say past performance predicts future performance, right? Yep, future success. Yep. You did? Yes. Here we go. Yeah. I have like 3 boxes.
Yeah, but it's actually the house.
Less trust.
Oh.
Yep, that's true. That's rough. You cannot extrapolate. So if there was ever a question on an MCQ and it was like, yo, tell me what the predicted value would be. Okay, you can't extrapolate. Okay, now we can take a guess, but it's not going to be something that is truthful, if you will. Okay. All right, number 5, what is the y-intercept of the equation of the regression line? That's going to be 25.33. Okay, and that means that at 0 rubber bands, predicted travel is 25.33 centimeters. That means that when we throw her off the balcony and we don't put any rubber bands on her, she's gonna fall 25.33 centimeters. So like you tie them together and it's like a bungee cord. Yep. Okay. What is the slope of your regression line? What's the other number in the equation? Okay. Okay, so the other number in this equation is our slope, so 7.46. And what does it mean? That means that one rubber band added a distance traveled increases by 7.46 centimeters. So now you get to learn about these cute little cutouts. Yay! Computer output for the regression line. Label values that you recognize. So they tell us that 7.46 is right here. This is your B value, if you will. This is your A value. The reason why we want to label this like this is oftentimes this is your linear regression line. Y equals AX plus B. You learned it back in algebra. It's just been a minute since you've seen it. Okay. This is y-intercept. This is your slope. This is your x. This is your coefficient of determination right here. Coefficient of determination. Plus. B and slope. All right, go ahead and flip over to the back while some of you are finishing up. I just work here. I don't make the rules. All right, so I am about to be 31. Yeah, bro. Saturday. Thanks, homie. All right, yep. Michael uses his Apple Watch to keep track of his distance and the number of calories he burns for 20 training runs. A scatter plot, calories burned, and X equals distance in miles shows a fairly strong positive relationship. The regression equation is here. It's a good model for the data. Interpret the slope of the regression line. So, for each what? Yes.
How many miles are in the training run? Because it says that he took 20 training runs, not that he ran 20 miles. And in every course talks about miles, but he only trained. And we don't know that each training run was a mile.
Okay, but you see that's where the scatter plot comes and how we have a nice variable because he does different distances.
So I would assume that 0 miles, right? How many calories does he burn? Okay. So at 1 mile, how many calories does he burn?
You're right. 20.
Okay. So we go based off of that. I see your point, but I feel like it's you want to look at what your X and Y are. They throw in some crazy tomfoolery in here always just to throw you off.
I'm just like, is if technically the data that's given is it miles? It's training.
Well, but I mean, you can run a mile one day and burn only like 50 calories. The next day you do 100 calories based off of your amount of water intake, etc.
You make a little square with a little finger. And the X, like each X isn't a mile. It's training.
Because okay, he runs those 20 training runs. He runs a different number of miles. Their training runs.
It was a different number of miles.
You don't need to go for marathon or as well.
I never said that. All I'm saying is that the variable is last time. There's no difference.
Last year.
Wait,
It's not how many training runs he does.
it's
How
the amount
many
of miles, right? But however, we weren't given the amount of miles, we were given the amount of training runs.
Because he has the wrestling equation to say what the mile is for that.
That's all we have to pay for his training runs.
So if he was to do on one of his days, a 2 mile run, we would plug in 2, we would figure out how many calories he burned. It's just giving you more information than necessary. So disrespect the lion like that, Mo, ever again. All right, ready? Let's try it. Okay, so interpret. So for each, I was telling you, homie. Yes, it was. Tell your mom. So for each additional mile that is ran, I'm reading and writing. The predicted number of calories burned increases by 160 calories. So if homeboy shows up and he does 4 miles, okay, we're gonna have 4 times 160. That's how many calories more he's going to burn. Cool? Okay, cool. Does the value of the y-intercept have meaning in this context? If so, interpret the y-intercept. So when Michael doesn't do anything as a lazy bum and runs 0 miles, I say that, I haven't been to the gym in like a week, runs 0 miles, I know, but like even still, predicted number of calories burned is 20. Right? What are you saying, Mo? Mo, you need the lion thrown at you again? Okay. Zach will get you. Okay. All right. So the predicted number of calories burned if he runs 5 miles. We're gonna plug 5 into our lovely equation. So when you do this, I forgot to mention this earlier. Just get the cute little hat. I know. So cute. 20 plus 160 times 5. And that's gonna be 820 calories. Ta-da. All right, calculate and interpret the residual if his Apple Watch said that he burned 760 calories on a 5-mile run. That would suck, yo. Your Apple Watch doesn't do as much as your, actual running. So we got 760 minus 820. That's negative 60. That means that the actual number of calories burned was 60 calories less than predicted for a run of 5 miles. Now, Michael is thinking about signing up for his first marathon. Don't do it, Michael. So far, his longest run has only been 10 miles. Should he use the regression equation to predict how many calories he would burn if he runs a marathon? Should he use the regression equation? That's extrapolation. So should we? No. Good, class. 26.2 miles is far outside the data he collected. Hey, friend. Thank you so much. Bruno, you're in trouble. Thank you, collectively. Thank you. So this is extrapolation. Hey, you're not in trouble, but at the end of the block, you're gonna go to the front lobby. Here, come get this pass though. I don't want it because I'll forget. What, David? What's up?
So,
Hang on now.
End of the block, Bruno.
how do you know this is 26.2 is outside of the rank?
Because he's training, and it said that he's never ran more than 10 miles.
Yo. Okay.
By the way, training for a marathon is a good idea if you're gonna do a marathon. because I didn't. And then I decided to go run a marathon off of 30 minutes of sleep after finishing my final paper for my master's. Did I finish? Yes, I did. That's all that matters, huh? So there were two marathons going on at the same time. So guess who got lost? Me. Guess who ended up running 31 miles instead of the 26.2, which means that I did an ultra marathon and technically could have qualified for like the ultra marathon like thing. I was so bad. It was terrible. I will not be doing that again. It's like it's done and we're not doing it again. So it was the one in Helen. So it was up a mountain and down a mountain. Terrible time. In Helen,